Hello, everyone. Good evening, and welcome to day 2 of this workshop on space robotics organized by SEDS-VIT and Spaceonova. Yesterday, we had the introductory session on space robotics, where we learned about types of robots, applications of robots in space, and the future of space robotics. Today, we will be learning about ROS. So, without any further ado, over to you, Mr. Sautik Nandi. Hello, am I audible?
Yes, am I audible?
Okay, yeah, you're audible.
Okay, perfect. Okay, so right now, just give me one moment. Right. Okay. So let's see how many people have we got today. And today we have about 50 people, where yesterday we crossed the maximum participation, and this time it's exactly half. So first of all, thank you everyone for attending today's session. And today we are going to see all about ROS and what ROS is and everything about ROS. And we'll be, and this is kind of an hands-on session. And as I said, that for ROS, we'll be needing an Ubuntu system. Okay, so you can either go about for installing of Ubuntu on your systems either through dual boot or through your virtual machine. It can be either of the two methods. Anything is possible, and you can run two operating systems on your laptop very easily. There are no, what do we say, there are no restrictions any whatsoever that you can only have one operating system. No, you can have two, you can have multiple operating systems as well on your laptop. Okay, so you can do that, but the recommended is a virtual machine if you're beginners, if you have just, or if you have no experience with dual bootings, just go for virtual machine. But if you're already pro and you already have or worked upon uh, you've already worked upon dual boot, then go ahead with the dual boot as well. And along with that, I was informed that few people were not able to register uh, on the registration form. So I will be dropping the registration link on the WhatsApp. So in case you have not filled up the form, please go ahead and fill up. Please go ahead and fill the form in case you have not. I have dropped it on the WhatsApp. So in case you have not filled up the form, please go ahead and fill up the form. And with this, we can begin with today's session. Let me just go ahead and present my screen, and we would be beginning with the session. Well, it's kind of divided into two parts. The first fragment would be all about the theoretical part as to what it is and what you're expecting. And then on the second part, we'll be directly moving on to the coding aspect, okay, where we'll be seeing how you can do things yourself. So let me just go ahead and present my screen, entire screen, and perfect. So I hope my screen is visible. So can you know if you just tell me if my screen is visible or not?
It's visible.
Okay, perfect. Thank you so much. So welcome to Space Robotics Workshop, day number 2, where we'll be learning about ROS and what ROS is. Well, ROS stands for Robot Operating System. That is what is the full form of ROS. And ROS is basically something of a middleware and a framework. So it is somewhere in between of a middleware and a framework, which is built especially for robotic applications. And with what goal ROS was made is that it would provide a standard for robotic applications, and it can be used in any robot. Well, let me break this down for you. So let's say that you have multiple robots, okay? You have one robot, which is, let's say that this is a tiny robot which you're having. Then you have a huge humanoid. Then let's say you have a mechanical arm. Okay, so you have 3 robots, and you have written a code for, let's say, grasping an object. Okay, so the same code can be used in your small robot, in your humanoid, or in your robotic arm. So you can use the same code in all of these 3 thanks to the robot operating system. And it's in standard so that all robotic applications can be used on ROS. So you don't have to forget about the rest of the stuff because you have the same code running on, or you have the same code which can be used in all three of them. Not only that, let's say that you have maybe made different kind, or you have used different languages for writing a particular piece of code. That is all perfect with this ROS because it does not have any preferred language. So you can use any language you want for writing codes. Okay. We will be seeing a bit about what ROS is and why do we use it. So let's move forward with why ROS. Let's take that you have a robot over here, and this robot is say robot R, and you have written, or you want your robot to do certain things. You want your robot to do motion, then you maybe want your robot to do camera, maybe then you have one for maybe GPS, then you have something for, let's say, speech, and so on and so forth. So you are having a total of 3, 4, 5, 6, or maybe 7 components which you want to integrate into this robot. Okay, you have 7 components which you want to integrate within this robot, and these 7 components could maybe intercommunicate with each other, provide data which can be used in somewhere else, and provide and receive data from some other component as well. So you want all these things to happen. Now just imagine writing all 7 of them in a single file and feeding it to your robot. Imagine the number of lines. It would be easily over 1000 plus lines for writing all the 7 components. Okay, so what we have done, we have taken the same thing, but we have divided into 7 components. And each of these components is known as a node. So that is what a node is in ROS. It is capable of running itself, and it is known as a node in your ROS. Now, once you have defined 1, 2, 3, 4, 5, 6, 3, 6, 6 or 7 nodes, then all these nodes would communicate with each other through a ROS communication tool, which is right over here. So all of these nodes would then be connected to ROS communication tools, and this would then intercommunicate with your robot. Okay. With the help of ROS communication tools, this motion node can talk to the camera node, and the camera node can talk to the GPS node. So all these can happen due to the presence of ROS communication tools. Not only that, the second reason why do we use ROS is, let's say that for motion you have 2 objectives, one being obstacle avoidance and second being a line follow. So you want your robot to fulfill both of these. You want your robot to fulfill obstacle avoidance and you want your robot to fulfill line follower. Now just imagine writing the code for obstacle avoidance and for line follower. Okay, I mean, this would be a huge code which you need to write just for these 2 purposes. And there are so many other things which you need to do. Okay, so writing all of them would firstly consume a lot of time. Okay, to consume a lot of time. And secondly, is it necessary? Because don't you think that obstacle avoidance and line follower maybe it should be there because it's a common problem or it's a common feature every robot should have? And the answer is yes. You would make use of libraries. Okay, you make use of libraries, and inside these libraries, you already have the codes written for obstacle avoidance and line follow. All these are written inside a library. You just need to figure out how you can use this library to fit into your robot. So do you need to write the code for obstacle avoidance and line follow? The answer is no. You don't have to write code for obstacle avoidance and for line follower because there are libraries available on the internet which you can just download and make use of. Okay. Simple? Simple. Not only for motion, you also have for GPS and for other things as well. The library is available. You just need to make use of them. Now, let's say that you are not the only person who are writing all of this. You, along with your friend, are writing all the codes for this. Now, your friend is not a Python pro, he's a C++ pro. So he has written motion in C++ and speech in C++ because he's a C++ pro and you are a Python pro. So you've written camera and GPS, the code for camera and code for GPS in Python. Now, should be a problem because you're having C++, Python, and how would motion and camera interact? Because one is in C++, other is in Python. Okay, Python interaction understood. C++ understood, but C++ and Python interaction, well, that is also possible thanks to our ROS. thanks to our ROS, the communication between a C++ node and a Python node is possible because of ROS. It is not dependent on the language at all. Okay, so you can have all this as well. So summing up, what happens is your entire code is divided into different fragments, or these are known as different nodes, and each node can be written in any language, and these nodes can intercommunicate with each other very easily thanks to the robot operating system. Now, let's go a bit more deep into our node and what they are. So before we go on to nodes and what they are, I'll first go ahead and tell you about the ROS installation. Now for ROS installation, you would need an Ubuntu system. Okay, need an Ubuntu system and Ubuntu most probably 20.0 plus. Okay, so there are two versions available, which is 20.04, I believe, and the second version is 21 point something, I believe. So go ahead with the 20.04 version, as the 21 version is currently in testing form. So don't go ahead with the 21 version. Go for 20.04 version. And once your installation of Ubuntu is completed, either through dual boot or through virtual machine, you can then proceed with the ROS installation. So let me first go ahead and explain you about ROS and what are the different packages available for ROS. So we'll go ahead with wiki.ros.org/distributions, and inside the distributions, currently there are two forms of ROS, one being ROS noetic and second being ROS melodic. Okay, for people, I mean, if you would have started ROS earlier, you would have come across the term ROS kinetic and ROS indigo as well. Okay, but as you can see over here, it's written end of line date, which means that ROS kinetic, which you might have heard last year, is no longer existing because it has reached its end of line date, which was April 2021. That is last year. It has already reached its end of line date, and therefore ROS kinetic is no longer in the running. Similarly, ROS indigo is also no longer in running. Now, currently there are two, which is ROS melodic and ROS noetic. Okay. ROS melodic would again be inactive in just 1 year. So therefore, we will not be going forward with ROS melodic. And as you can see, ROS noetic is written the recommended. So we'll go ahead with the installation of ROS noetic. Now, once you have gone on to the installation, you would see that there is already written what is the correct installation procedure. It's already well written. So go ahead, choose your platform, and as you can see, it's written supported. You can have a Debian or an Ubuntu. And experimental is Windows. So if you want to go ahead with Windows 10 and proceed with the installation, you are free to do so. But please note, it's written experimental. So there's no guarantee whether it would work or not. Okay, so there's no guarantee. So it's written experimental, but it's very well supported on Ubuntu. So we'll go ahead and see the installation for Ubuntu. Now, for the installation of Ubuntu, what you need to do is simply copy paste each and every line. So you'll first copy paste your sources list, then set up your keys, then initialize the keys. Then you would go ahead with installing your ROS noetic desktop full, because it will have everything from your simulators, which you'll be needing for today's session, and also perception as well. So you would be needing all this thing. But let's say that currently you just want to test out ROS and you do not have that much of bandwidth available, or you don't have that much of data. So you would go ahead with ROS base. Okay, you have ROS base, which would only have the necessary packages and necessary modules just for your ROS to run. Okay, no graphic user interface, nothing, just pure ROS. Okay, as you can see, it's written bare bones. So you can go ahead and proceed with the ROS based installation. And further, if more, as we come across more packages, you can go ahead and install all of them using the same command sudo apt install ROS noetic the package name. As you can see, it's written sudo apt install ROS noetic package name. Let's say that for a simulator, we would be using Gazebo. So I'll just go ahead and write sudo apt install ROS noetic Gazebo. Okay. Simply, I would then install each and every package. So you can first start with your base, and then go ahead and install the packages as in when you need. That is how you'll be going forward with the installation. Once your installation is completed, you'll first source that into your bash RC for it to work correctly. Now, you can read the tutorial correctly and how it is saying. So what happens is every time you run a new shell, a .bash rc gets loaded. So if you already source your setup for your ROS Noetic, so you don't have to write it again and again, because once you're sourced into your bash RC, it will be run every time a new shell is launched. So that solves your problem of going ahead and sourcing it again and again. Now, once your sourcing of bash RC is done, there are a few more packages which you need to download. They are all the essential packages, as you can see. A few of them you need to download with the core ROS packages. Then after the core ROS packages are done, please note that there would be no reinstalling of a package. If a package is already there, you don't need to reinstall it. It will tell you that this is already satisfied. So you don't need to go ahead and reinstall it. Now, once everything is done, you can then just simply write ROS code, and that would make sure that your ROS is correctly installed. So in case you are currently on an Ubuntu system, and in case your terminal is open or was open, or if you would have tried, if your ROS installation is complete and it is working by writing just ROS code, go ahead, write one in the chat section so that I can get an idea of how many people have the ROS installation completed. Or in case you are yet to do or have not done, or there are any bugs, just write 0 in the chat section so that I can understand how many people are facing problem or they are lazy to do so. So either of the two, that is ones or 0, just write in the chat section, is your ROS working correctly? Write 1 by just writing 1, or write 0. The command for making sure the ROS is running correctly is ROS core. ROS, ROS, CORE, code, ROS code. All right. So that completes with the installation. My ROS is installed, and now it's time to go more deep into what ROS is. So first, I'll going forward with ROS node. Now, what ROS node actually is that for a ROS node to work, okay, for a ROS node or for a node to work in ROS, you need to have different packages. Okay, let's say that you have this package, and in this package, or you're having another package and you're having another package. So you have a total of 3 packages. Inside this package, you are having 2 nodes. Let's name this as package A. Then in this package, you're having 3 nodes. Let's name it package B. In this package, you're having just 1 node. Let's name this as package C. Now, for nodes to work, they need to be inside packages, and then the nodes can either communicate with each other through a package. Okay, so you can just go ahead and maybe they can communicate with each other inside the package, or they can then, or they can just simply, where's my book? Yeah, they can just simply communicate inter packages as well. Okay, so you can have this node from package B communicating to this node in package C, or you can have this node in package A communicating with this node in package B, or you can have this node in package A communicating with this node in package C. So you can have all these relationships established by creating ROS nodes inside packages. Now, you may not understand why we are having packages or why there are nodes inside of packages. Let me break it down further for you. Now, what happens is, instead, let's say you do not have these packages, you're having simple nodes. Okay, you're having these simple nodes. Now, it becomes very difficult for you to categorize these nodes. Let's say you're having one node for the camera, one node for the GPS. Both of them may come under the same package motion. So what you would do is that if you're searching for these, it becomes very easy if you keep them inside a package, so that you would know that, all right, this package is motion, so all these nodes inside of these are only related to motions. Let's say you have any bug anywhere which was related to motion, you can then simply just see, okay, this was this package, package name was motion, so you can just simply see that this is package motion, inside that these are these 2 nodes. So this means that there must be a fault in these 2 nodes. If these packages were not there, if all 3, 4, or all 6 of them were in the straight line, then imagine how difficult would it be to identify the bugs. Okay, maybe you may remember that, all right, camera, so this must be related to motion, but it becomes, or a task becomes more easier once they are categorized into three different packages. Once we have different packages, they have different nodes inside of them, and they can simply communicate with each other. That is how the ROS architecture was built. Okay, you have packages, inside of packages you have nodes, and these nodes can communicate with each other. Now you'll tell me that how these nodes would communicate with each other, right? For communication of nodes, we have something known as ROS topics. Now, what exactly are ROS topics is, before I go ahead with ROS topics, I'd like to first demonstrate, or I'll first illustrate what the process is all about. So what happens is, let's say that you have this antenna over here, okay? You have this antenna which is emitting radio waves, okay? And these antennas, this antenna is emitting radio waves at the frequency of 97.77 hertz. Okay, so this antenna is emitting frequency at 97.77 hertz. So let me just draw a line through them. Yes, so this is my antenna which is emitting frequency at 97.77 hertz. Now, okay, so my antenna is emitting. So there must be someone to receive it. Okay, there must be someone to receive this frequency. So you have a radio at your house, and this radio is already listening, or this radio is receiving from 97.7. So this is my signal, and the signal is being received by my radio. You would say that why only radio? I can have TV. Okay, and maybe TV is also listening 97.77. So my TV also listens to the frequency 97.77. Well, that does not stop here. You have Lightning McQueen, which also listens to 97.77 hertz. Okay, as you know, the Lightning McQueen likes to keep himself updated with the news, so he listens to news at 97.77 hertz. So he listens to this as well. Now, on the right hand side, you see that they are our receivers. On the left hand side, these are our emitters. You'll also notice that the radio does not know that TV is also listening to this, and TV does not know that Lightning McQueen is also listening to it. Also, Lightning McQueen does not know who is sending it, because in the point of Lightning McQueen, he's just only seeing that it's 97.77, which I need to subtract to. I'm not interested in who is emitting it. I'm interested in what frequency they're emitting it. So Lightning McQueen is just seeing 97.77, TV is just seeing 97.77, and the radio is seeing 97.77. Similarly, if you go from the antenna's perspective, the antenna is only seeing 97.77. That's it. He's not seeing that who else is there. Is it radio, TV, Lightning McQueen, or Lightning McQueen's partner? The antenna does not know, because the antenna's work is just to emit. That is it. And the work of radio, TV, and Lightning McQueen is just to receive. Now, the emitter and the receiver have the terms known as publisher. So this becomes a publisher because this guy is publishing, and they become subscribers. Okay, they become subscribers because they are subscribing to it, or they are receiving it. And the one which you're seeing right in the middle, 97.77, this is known as a topic. This is known as the topic. So you have publishers, you have subscribers, and you have topics. Not only that, it does not stop here. You can have another publisher as well. Okay, there is another publisher. I'm calling it P, and this publisher also emits at 97.77. Okay, because when Lightning McQueen is going through town A and town B, Lightning McQueen would see that this antenna is now no longer in range. Rather, this antenna would now become in range. Okay, so Lightning McQueen is still listening 97.77, but they are coming from different publishers. Okay, one is coming from publisher A, the second one is maybe coming from publisher B. Again, Lightning McQueen is not interested in which of the publishers they are, because he just subscribed to 97.77. That is it. Okay. Okay, so you can have any number of combinations as well. You can have the publishers publishing and no subscribers. You can have subscribers subscribing to a topic but with no publisher. You can have one publisher, one subscriber, one publisher, two subscribers, two publisher, one subscribers. You can have all the different combinations as well. Not only that, Let's say you want to just have another topic, which is 99.99, and this is a publisher, and Lightning McQueen is subscribing to 97.77 and 99.99 as well. Okay, so Lightning McQueen is currently subscribed to two topics which are coming from two different publishers. Okay, Lightning McQueen is capable of doing that as well. Okay, so that was about my ROS topics. And well, if say this is the frequency, then this frequency would obviously be very different from that of the previous one. And one thing which I forgot to mention is the frequencies which you are, or the ones which you are seeing, which I'm drawing from here and going to there, these are known as messages. Okay, these are known as messages which are transferred from a publisher to the subscriber via a topic. So if you want the, what do we say, textbook definition, the textbook definition is topics are named buses over which nodes exchange messages. Well, to break it down, topics are named topics, named buses. Okay, topics are named buses. So this I'm calling it 97.77. You can name it. You can maybe, let's say, instead of 97.77, I'm calling it topic. Okay. Instead of 99.99, I'm calling it SEDS-VIT. Okay. So I would simply say that Lightning McQueen is subscribed to SEDS-VIT. Okay. Lightning McQueen is subscribed to topic. Okay. So you can have, or you can name them. You can name the topics as well. So it's a name bus done over which nodes exchange messages. Yes, the nodes exchange messages over this topic. As you can see, this was a publisher which was emitting, or which was exchanging messages through my topic. And one more thing, this is unidirectional. So a publisher always publishes it, a subscriber always subscribes it. So this is a unidirectional flow. But this subscriber can again go ahead and publish it. Okay, so this becomes a subscriber and a publisher. Okay, it becomes a subscriber and a publisher. Let's say this radio is then connected to a phone. Okay, so then this would become a publisher, and then this phone would become a subscriber. Okay, so you can do that as well. It can become a subscriber and a publisher. Okay, so well, that was all about your topics, your different nodes, and topics, nodes, publishers, subscribers. Now that we have given you all the basic theory of what they are, now we can go on with the hands-on part. We can go on with the coding aspect, where we'll be seeing how you can use them on your system and make wonderful things. So for that, I'd like to invite Anshul, Mr. Anshul Raze, who is currently an innovator in the Department of AI, to proceed forward with the session and move ahead with the coding part. All right. So Anshul, you may now proceed.
Yeah, thank you, Sathik. I'll present my screen. Okay, is my screen visible?
Yes, Anshul, it's visible.
Yeah, okay, thank you. All right, now, so after you have dual booted, or you're using VM, whichever option you choose, and after installing ROS, let's actually start working with ROS. So firstly, we need to create a Catkin workspace. Now, what is a Catkin workspace? It is just a directory or a folder in which all of your files and folders related to ROS live. You need to have a Catkin workspace to be able to use ROS. So let's start with creating that. Open your terminal or your Terminator. I'm using Terminator in my case. Both work just fine. Now, in your home directory, let's type mkdir -p workshop _ws/src. So in this, mkdir is just the command for make directory.
Can you zoom in a bit, please? I think it's small. A little more. A little more. I think that's perfect.
Right? All right. Yeah, so now mkdir is just make the command to make files or make directories. Workspace _ws is the name of our folder, and src is a folder inside this folder. So after we press enter, and if we ls or list all of our folders that are currently available, we can see that workshop underscore ws was created. And now we can also ls the workshop directory itself, and we'll see that the source folder is also there. So now let us cd or change directory. Let's enter our workshop directory. And now as you can see, we're currently inside of our workshop directory. And now let us run catkin underscore make. Now this catkin underscore make command just automatically builds the workspace for us. By the term build, I just mean that it will automatically create the default files and folders that are required for a workspace to function properly. We don't need to worry about what these files are. And so if I ls again, we'll see that there are two new folders. There's build and there's devil. And like I said, we don't need to worry what's in this. And now let us source our generated setup file. And we do this just to add our newly created workspace to the ROS environment. So source space slash devil slash setup dot bash. Okay, so we don't have any errors, so it got sourced. And the next step is for us to create a catkin package. And now what is a catkin package is basically what Sautik said. It's just a subdirectory that contains most of our main code that you want to run. Now you don't necessarily have to have one package for everything. Well, you definitely can have one package for everything, but in practice, it's better to have multiple packages for various tasks, for motion, camera, path planning, so on and so forth, just like Sautik said. So let us enter our source folder. As you can see, we are inside our workshops folder and our source folder. And the command to create a catkin package is catkin underscore create underscore pkg or package. And don't worry, this is a lot of commands. I know there are a lot more commands that we need to do. We will share a GitHub repo which will have all of these commands listed and what they do. So catkin underscore creator underscore package. And now let's give our package a name. I'm just going to name it workshop. And everything that comes after the name is called the dependencies of the package. Dependencies, as the name suggests, are the libraries that the package quote unquote depends on, or more specifically are the libraries that we can import in our code. So the first one we want is ROS.py, which is just ROS Python. Then we want std underscore messages and geometry underscore messages. These are two different message types. I'll explain what these are in a bit when we're actually coding. So let's press enter and our files were successfully created. Okay, so now let us go back to our workshop main folder and let us run catkin make again since we made a new package. Okay, cool, it is created. You guys can ignore this warning, by the way. And I'll get this warning, you guys won't. So let us run the source command again, which was source devil slash setup dot bash. Okay. And now let us code our first node. And you guys can use whatever text editor you want. I prefer to use VS Code, so I'll use VS Code. And now let us open a source folder. This is a little small. I'll show you what I'm talking about in a bit. Okay, so if I do ls, we can see that there are 3 folders. I'll go into the source folder. And if I ls again, we'll see our workshop package, which was created. So let's go into our workshop package. And if I check which files are under this again, you'll see that there's another src folder. So this is the src folder that we are writing our code in. It is not necessary to write all of our code into this and store it in this, but it is convention to do so. So let's do that. And let's stick to convention. So this is the file that I've opened right now. And in our src folder, I'll create a new file. Let's just call it node.py. Py is the extension for Python. And wait, I'll zoom in for you guys. And okay, so let's start coding our first node. So the first line in every Python file will be something called the shebang line. The shebang line just tells our interpreter to interpret the code in Python 3. Ubuntu 20.04 usually comes pre-installed with Python 3.8, so we will write Python 3. So it'll be hashtag exclamation mark slash usr slash bin slash env or environment space Python 3. Now remember, this line needs to be there in every single Python code that we write. This has to be our first line. If we do not give this our first line, our system will be confused about what we are interpreting, what is the code, and what is the language. Okay, so now let us import a library. Let's import ROS.py, just for ROS Python. And now I'll write if __ name is equals to __ main. Now what this line does is that it makes sure that the code is only executed when the file is run directly and not when it's imported. So if in another program or another node, we import this file, it won't run automatically there. It will only run when we are running this, when we are executing this code directly. So after this, let's initialize our node. So let's do ROS. The command to initialize our node is rospy.init_node. And let us give our node a name. I'm just going to call it node for now. Now let us show that our node is active. So let's actually print something. Let's print node is active. And let's also print shutting down. So after this, let's save our file. And now we are going to give it executable conditions. So let's go into our source folder, which has our executable over here. And now, as you can see, it's white. The command to give it executable conditions is chmod +x space the name of our file. So just node.py. Now, if I list the files again, you'll see that our file is green, which means that it is an executable file. Now, I'm going to open another terminal, and there we need to have a ROS core running in the background all the time. The ROS core is just something that tells other nodes where it is in our ROS environment itself. If we do not run a ROS core, then our nodes are not going to be able to run. So let's just run the ROS core in the background. Okay, it's running. I'm going to minimize this. And now let's go back to our main file. And let's source again. Source devel/setup.bash. And let's do ROS. The command to run our files is rosrun. Rosrun space our package name. Our package name was workshop. And our actual file, so node.python or node.py. As you can see, our node got activated, but it instantly got shut down. We do not want it to instantly shut down. So what we're going to do is, yes, we have successfully initialized a node, but we successfully initialized it and it instantly shut down. We want it to shut down only when we tell it to shut down or when we force it to shut down. So we're going to add a while loop over here. So while not rospy dot is shut down. So what rospy dot is shut down is just a function that checks if our ROS is shutting down. So not shut down is that if it is not shut down, that is if it's active, run all of these codes. So let's put this into the while loop. I'm going to take this out of the while loop for now because we don't want it. We only want it to show shutting down when we actually shut it down. So now let's save this again. And let us run this again. ROS run space workshop space node.py. as you can see, okay, so the node is active, it is not shut down, but we are printing an infinite number of node dot active, and it is like printing it insanely fast. This is also something that we don't want. So if you want to exit the node, if you want to shut down the node, the command is Control plus C, then Control plus C. And if you want to force shut down a node, it is Control plus Z. But always try Control plus C first. If Control plus C is not working, then do Control plus Z. So I'm going to clear this. And now we want our node to print, node is active, but not infinitely. We want it to print at a certain rate, or we want it to print in a uniform manner after a certain time. So let us define a rate in our node. So I'll type in the code and I'll explain to you what it is afterwards. So rate.rospi.rate1 rate.sleep. So what this does, this is just I am just creating a variable of type rate, who has 1 as a parameter. This unit is hertz. So 1 hertz means that this node or this code will run at a rate of 1 time per second. If I put 2, it will be 2 times per second. 3 is 3 times per second. So I'll just keep it at 1 right now. And rate.sleep just executes the rate. It pauses this program for however duration it needs to, right? So that's what sleep does. It takes so let's save this and let's run our node again. See, now it is not printing it infinitely, it is printing it at a rate of 1 per second. Let's change it. I'll Control C again to close it. See, it says shutting down because I put shutting down outside of our loop, right? So as soon as it realized it's shutting down, it exited a loop, it printed shutting down, and everything stopped. So I'll change this to 2, or let's change it to 3, and it should print at a much faster rate. Yeah, see, it's much faster than it was before. So that's what rate and rate.sleep does. It just pauses our program so that we can print it at a certain hertz, or we can run the code at a certain hertz. So I'll clear it again. And now we have successfully created a node. And now let's get on to creating a simple publisher and a subscriber, right? So I'm going to create 2 new files called publisher.py. Now create another one called subscriber.py, right? See, and again, so let's start coding our publisher. The first line in our Python files should always be our shebang line. And these first 3 lines are the same. So I'm just going to copy paste them. It's our shebang line, the import rospi, and then the if name. We need to import another thing. The thing we need to import is our message. The message is what we use to talk over our topics. So from std_messages, if you remember, we had put this as a dependency, .message import string. So std messages is just a library of multiple message types, out of which string is one of those message types. So if name, I also need the while loop again. While loop rospi dot is shut down. Okay, let's initialize our node again. Rospi dot init node. Let's just call it a publisher. And publisher. Then let us create a variable of data type, our message type string, right? And now this message type, it is not a variable on its own. It has its own subvariables. So string, I'll just write string.data for now. .data is equals to hello world. I'll explain to you what .data means exactly when we're running our subscriber, and after we're done with that, I'll explain what that is. string.data, and let us actually now create a subscriber. Let's actually create a publisher, right? So we need to create a variable of type publisher. Publisher is equals to pub is equals to publisher ross.py dot publisher. So we have created a variable of type publisher. And now our publisher needs three arguments. It needs what topic we are going to publish to. It needs to know what message type we are using, and it needs to have a queue size. So let's say we are publishing to a topic named just chatter. Then we need to give it what data or data class is doing. We have string, right? String over here. And now a queue size. A queue size just acts as a buffer so that if our program gets paused or if it gets stuck somewhere, then we won't lose data. Our last 10 publishing data will get stored in this and it will get published sooner or later. So we don't lose data with this. And now let us, again, as we saw in our node file, we didn't want it to publish infinitely. We gave it a rate, right? So let's give this a rate as well. Rate is equal to rate. Rate is equals to ross.py dot rate. Let's do 1 per second. Then rate dot sleep. Right. So this is our publisher done. So let's get on to our subscriber. Again, it has the same 4 lines. We want our message type as well. So I'm going to copy paste the 4 lines. And then let us do ross.py.init underscore. Let us name our node subscriber. And let us define this as a subscriber itself. So ross.py dot so not subscriber listeners, subscriber. Again, this needs 3 arguments. What topic it is subscribing to. So in our publisher, we are publishing to topic chatter. So this needs to subscribe to topic chatter as well. So chatter, it is of data type string. And our third argument is not queue size. It will be something called a callback function. Now, a callback function is just a function that will be triggered when messages are received. If you don't use a callback function, sure, our subscriber will get new messages, but we won't be able to do anything with the new data. So we do need a callback function. So I'll just call it a callback. I'll define the callback function later. And let's say and our last line will be ross.py.spin. Now, ross.py.spin simply just keeps our node from exiting until our node has been shut down. It is why we don't exactly need this while loop. ross.py.spin does not the exact same function, it does a similar function. Right, so ross.py.spin will just prevent our node from exiting until we shut it down. So after this, we need to define our callback functions. Let's do diff callback. And we will be receiving some data over here, right? Now let us just print this data. Oh yeah. So now we're done with our publisher and subscriber. Again, let us give them executable conditions. So, or permissions. So cd source / our package workshop, the source. Both of them are white. So chmod +x publisher and subscriber. Okay, both of them are executable. Let's go back to our workspace folder and source devel/setup.bash. Clear, cool. Okay, now let us run both of our publisher and our subscriber. Ross run workshop publisher.py. Ross run subscriber. Oh no, so not subscriber. Workshop, our package name. Oh, I need a source over here as well. Sorry. Source devel slash setup dot bash ROS run workshop subscriber.py. Yes, I'm gonna restart. Okay, ROS run workshop publisher.py ROS run workshop subscriber.py. And why is it not printing?
Just check if you started the publisher.
I have started the publisher, yeah. Workshop subscriber.py. Yes. I forgot to publish my actual data itself. Sorry. We need to actually, obviously, the subscriber needs to be able to publish something. I mean, the subscriber needs to subscribe to something. But if the publisher isn't publishing our actual data, then it's never going to subscribe to anything. So let's do, to actually publish, just do pub.publish, and let's publish our string. Okay, so everything should be working fine now. Let's do ROS run. Yeah, see, now we are actually, so our subscriber is subscribing to the topic chatter, and it is printing out the data. And as you can see, it is saying data : hello world. So that is what I meant by it is a subvariable in our publisher data.data. So if I want to get rid of this data thing, I'll just do data.data. I will access the sub variable and print that data itself or that message itself. So let's Control C. And see, now we're only printing hello world. We're not printing data itself. So that's what I meant by it's a sub variable. We will, this string message type had only one sub variable, but there are multiple message types. We will look at one called twist, which will have 6 sub variables. There are ones which have 13 sub variables. There are a lot. So this isn't the only thing. And now I'll also show you this command called ROS topic list. Oops. So if we do ROS topic list, we will see that our /chatter topic is active. As soon as I shut down our nodes, our publisher subscriber, and I run this again, see, ROS chatter is no longer there, right? So yeah, we have written a very basic publisher and subscriber that we can create right now. If there, we'll take a little break, and if there are any questions, you can ask.
I think Anshul, I mean, currently we are already running out of time, so we can just proceed forward, and then in the end we can do the question and answers. All right?
Okay, we'll start running. Okay, yeah, we'll get working with Gazebo now.
Yes. So we can just,
yeah, we can go with Gazebo. So now, as I said, these are the very basic publisher and subscribers that we can create. We are now we're going to do something a little more with the publisher specifically that we just learned. To do this, we need to install Gazebo and Turtlebot 3. So Gazebo is just a robot simulator. Turtlebot 3 is a bigger and friendly robot model that we are going to use now. And I won't show the steps to installing Gazebo and Turtlebot because one, I already have it. And two, it will take 10 minutes to install if you run that command. But in our GitHub repo, we have steps to run and install Turtlebot. So you just need to run all of these commands and then Turtlebot and Gazebo both will be installed. So I'll show you an example of our Gazebo. ROS launch, Turtlebot3 Gazebo, Turtlebot3 empty world.launch. So this is our Gazebo simulator. This is our Turtlebot that we will be working with right now. So I will, again, let's create a new window. Zoom in. Let's do a ROS topic list. Now you can see there are many more topics that are active currently. Yeah, before there were only 3, including our chatter. So the one we are interested in is CMD_vel, or its full form is command_velocity. So based on whatever values we publish on this topic, this robot will move. So that's what I meant by we're going to be doing something with a publisher. We're going to be publishing values to this topic to move this robot in a certain way. And now let's say that we want to move this robot in a circle of some radius. So let's get started with the code for that. Let's create a new file called circle.py. And again, our first line needs to be shebang. And if name, actually we also need the while loop. So let's copy paste this, put it in our circle. We need another message type. We don't want string, we want twist, the one I was talking about earlier. So let's do from geometry messages. We put this in our dependencies, .message, import twist. I'll explain what all is in twist in a bit. So let us initialize our node again, rospy.init node. Let's call it circle. Then let us create our publisher. Pub is equals to rospy.publisher. And now again, our 3 arguments were what topic is it publishing to, what is the data type, and a queue size. So again, the topic we want to publish to is CMD_vel. So we will write this over here, CMD_vel. The data type is twist, and our queue size is, let's say, 10. Queue size is 10. All right, now let us create a variable of message type twist. So as I said, every message type has its own subvariables. String only had one subvariable called data, so we did string.data, right? But in this, the twist has 6 different subvariables, which are split into 2 groups. It is linear velocities and angular velocities. Linear velocity has XYZ direction, angular velocity has XYZ direction. So it will be vel.linear dot something dot x or y dot z. I'll explain what it is in a bit. Vel dot angular dot some x, y, or z. I'll explain which ones we need in a bit. So how will we get this robot to spin to drive in a circle? Well, we know the formula V is equals to R omega. And let's say we want to drive it in a radius of, say, 2 units, right? So V in this formula is our forward velocity. So we want, it is our forward linear velocity. So we want vel.linear.x. We want a linear velocity in our forward direction, which is x direction. So let's define this as some 0.25 units. And we want omega, which is our angular velocity. In our frame of reference, we want the z-axis. So we'll do angular.z. And to calculate what omega we need, we'll just do v divided by r. So 0.25 divided by our radius. And let's make sure that I actually publish these values. So pub.publish our val. So there we go. We've written a code to get this running in a circle. Let's test it out. I need to give it executable permissions first. So cd source /workshop/source ls. Let's chmod +x circle.py. Okay, it is an executable file now. Let us go back and let us run our source command /dev/setup.bash. Okay, cool. Now our robot is active. Let us do ROS run our package workshop, and let's do circle.py. As you can see, it will start curving over here. It will pass through this, which is a circle of 2 radius. So yeah, that's about it. In this workshop, we learned what is ROS, why is it needed, how it works. We learned how to make a node, a publisher, a subscriber. We also drove this turtle bot in a circle. So it reached the halfway point. This was the origin. It passed through here. Will pass through here, and then it will come back. And yeah, to conclude, I'd like to show you that this is not the limit to ROS. There is a project that me and a few friends have done. I'll show you. So let's shut this down. To reset this turtle bot, you need to do Control+R so that it comes back to its position. And there we go. I'll do ROS run. My package is controls_ROS and sign.py. So this is a path following algorithm that calculates lateral and angular errors from a desired path and automatically does its own calculations to steer the robot onto the said path. So let's run this code and open Gazebo. And the path we have given it right now is a sine wave. And to remind you, the robot is making its own calculations based on its current position and where it wants to be. We are never telling the bot to go forward at a certain velocity or turn at a certain rate. So like how in our circle, we've defined it as 0.25 and we've given it this calculation 0.25 divided by radius. We aren't telling the bot to do that. It is making its own calculations. It is figuring out what forward velocity it needs to go. It's figuring out what angular velocity it needs to go. And so yeah, let's wait for it to finish. And okay, so it reached. The yellow path is the actual sine wave or the sine path we wanted to follow. The black curve is the route or the path that the robot actually drove. So yeah, that concludes our workshop. If anybody has questions, you can ask me.
Right. So before we move forward with the question and answers and the rest of the part, because I believe that you must have a lot of questions. And yeah, there are a lot of things which you can do. I'd like to invite Dr. Shreya Shatra, who would be right. So I'd like to invite Dr. Shreya Shatra for telling us more about not only about ROS, but also how you can extend the same thing into the space part and all the rest of the things. So Dr. Shreya Shatra, I think it would be great if you could address our audience.
Hi, thank you, Satik and Anshul, for the great presentation and also for teaching so much about ROS. So, and I'm really thankful to SEDS-VIT for this workshop and for all the participants who have been here for these 2 days. I'm sure you enjoyed, but this was just a teaser. So we are launching the space robotics course in March, 6th of March. And there you'll have, it's a 1-month training program. So you'll have much more topics related to space robotics, which we will cover, like also designing and testing and qualification. Of course, ROS coding and programming and how ROS is more helpful for also space robotics, and also we will have some AI and control lectures by some other space robotics experts. So we hope like you'll be joining the course, and you'll have fun learning something new. Yeah, thank you.
Right. So thank you so much, Dr. Shantara, for the wonderful, or giving us the participants an insight as to what is in store for them. What is the surprise, which we were actually saying in the previous days as well. So that is what this store for you. And in our training program, it's just a basic crux of we're just giving you a basic idea of what we all can do. I mean, we just saw that how, or we already had a pre-made small turtle bot and we were trying to control them. But once you go on to the training program, you'll studying all these things rather deeply, and we'll be moving ahead with more complex things, and how this thing can then be explorated into space and what all. So all this information and everything we would be sending you. Okay, we'll be sending you on the group itself and also on your email IDs. Everything in detail would be given to you so that you guys have an idea at what all is there in our training program. And with this, we would like to conclude this workshop. And yes, we'll go on to the question and answers as well. So thank you, SEDS-VIT, again, giving us a wonderful opportunity for presenting the Space Robotics Workshop, a 2-day workshop for the participants. Okay, so thank you so much. So now we can proceed with the question and answers. So guys, if you have any question and answers, please mention them in the chat, or you can just simply switch on your mic and ask us. I think the first question which I would, or you would ask me, is that where is the link of the resources, right? So just give me one moment. I'll share you the link on the group itself. It's spacerobo.com/space robotic resources. So let me just go ahead and share the link. There you go. So in that link, you would have firstly a small basic tutorial. Okay, there would be a tutorial about the basic commands, what they are, and the definition of the commands. Along with that, whatever code which you are seeing right in front of you, whatever we have coded, it's all there in the GitHub repository. You simply go ahead, download all of them, play on your systems, and then come back to us if you have any questions. Madhushri is asking that do we have certificates for the workshops? Yes, sir. Yes, Madhushri, you have the certificates, and the certificates will be dispatched in 7 days from today. So you would be seeing, or you'll be getting your certificates on your email IDs only. Okay. In case you're having trouble finding them, it would mostly be in either in spam folder or in the promotions folder, either of the two. But we shall be notifying them on the group itself as soon as we uh, release the certificates. And yes, the WhatsApp group link I'll be sharing again in the chat for the people who are yet to join. Okay, so don't worry about that. And if you want more details on the space robotics training program, we would send you on your email IDs only. Okay, and on the group as well, we'll be sending the brochures as well as the register, all the details, everything, we'll be sending them. Okay, no need to worry about that. Anything else? Do you have any other questions from anyone? So I've given the WhatsApp link in the chat section, and it seems that no one has any more questions. So thank you so much again, SEDS-VIT, for giving us the opportunity. And yeah, you can then go ahead.
Yeah. So first of all, I'd like to thank Spaceonova and their presenters for conducting such an amazing and informative session. We hope we can do more collaborations like these in the future. I'd also like to thank all the participants for joining today. We hope this was fun and you learned a lot about space robotics and ROS. We look forward to seeing you guys attend future sessions organized by SEDS-VIT. Do follow us on our Instagram page at SEDS-VIT for more information on events and recruitments. Once again, thank you all for joining. Have a good night and stay safe.
Bye bye.
Bye.